Citus. I was a software developer at Amazon.
Mike.
Yes.
Don't use the mic. Fuzzy, bad, unreliable. Okay.
Yes.
So let's use the one that doesn't say that.
Hello? Cool. Hey, I'm Ozgun. I'm one of the technical co-founders at Citus Data. Prior to Citus, I was a software developer at Amazon.com. That's how Jason and I know each other. And today, Jason and I are going to co-present PG Shard, a sharding and scaling extension for Postgres. The talk has 4 sections to it. First, I'm going to motivate PG Shard. And then I'm going to talk about the use cases where it's applicable. Then I'm going to talk about the data, how we use logical sharding to shard out the data to dynamically scale out the Postgres cluster. Next, Jason is going to jump in, and he's going to talk about the magic that makes all of it happen. What happens when you send a query to the PG Shard cluster? How do we route the query? What do we do when there are failures in the cluster? And finally, Jason is going to conclude the talk. We have about 35 slides, some of them animations. This is a fairly technical talk. If you have any questions or any feedback for us, because we're looking for feedback here, please feel free to ask your questions or give us your feedback. So first, I'm going to give one slide to put things into context, and then also motivate the talk afterwards. Prior to the talk, how many of you guys have heard of like a Citus DB? Okay, fair number. And just to clarify, Citus DB and PG Shard are separate products that complement each other. PG Shard targets the use case where you're doing short reads and writes, real-time reads and writes. So it's more targeted towards the NoSQL use case. And Citus DB is more applicable when you have lots of data that you want to analyze. You're running ad hoc analytics, real-time analytics on top of your data, and now you want to parallelize those queries across in your cluster. Citus shards your data in much the same way PG Shard does. The shard names, the table names, the metadata is all one and the same. That's why the two products are compatible with each other. It extends PostgreSQL, so it's not a fork of PostgreSQL. That way it gets to support new data types and extensions such as PG Shard too. And the reason I put that slide up is we initially started out as saying Citus DB enables only batch loads. So if you have your database, you can run your select queries and then will parallelize, you'll have real-time reads for that cluster, but we didn't support to begin with the real-time ingest path. And we had one customer, I don't know if they're here, who came to us and said, can I do real-time inserts? And we're like, we're sorry, we don't support that functionality. And they're like, isn't this Postgres? And I'm like, yes. Isn't this where the metadata is? Can't I just build my own library to do the routing logic itself? And they went ahead and did it. Then we had a second customer who asked for the same thing and built the same thing. And by the third customer, we got the hint. So we then took a step back and we're like, yeah. Oh, one of those customers is here. And so we then took a step back and started talking to PostgreSQL users who have lots of, who have big data sets. Kind of like a survey as to what it is that they're doing right now when they reach that scale. And there were 2 themes there. One theme was people were looking to do sharding at the application layer, so roll in their own sharding mechanism. That's a fair bit of effort, and it requires a good understanding of distributed systems. How you replicate the data, how you handle failures. A second group of people were looking to, as much as they love PostgreSQL, take a dump of their data, denormalize their tables, and then load it back into a NoSQL solution. Obviously, you're giving away a good chunk of functionality there. Still, if you don't want to deal with the distributed systems problems, this sounds like one way to grow. So we took that even one more step further, and we're like, okay, if you had the ideal PostgreSQL scaling solution, what are your top 2 or 3 asks? Obviously, the top 10 list is a big list, so it's hard to find common themes there. If you hammer it down to the top 2 requests, there are, like, things become more common. The first one is dynamically scaling up the cluster. People were saying, I don't want to think about, I have 5 machines and I have another machine, and then I need to now rebalance my cluster. I want it to automagically work. Similarly, if I lose a machine in the cluster, I don't want to go and do all this extra effort. I want the cluster just to keep running. So kind of like magic, like magically scaling out and magically handling failures. So that was like top feedback number one. A second ask, or a second wish, if you will, was it should be easy to set up and use. I don't want to set up multiple components. I don't want to configure all these components together. I just want to use this on my PostgreSQL version. If I'm using Postgres 9.3, good, 9.4, I want to get that functionality. And a third, I wouldn't say an ask, but a third theme was for a good number of people, transactional semantics weren't as important. And when I say transactional semantics, I'm thinking of the financial institution use case where you have, let's say, accounts, and then those accounts live on different shards, and you want to start a transaction, you want to debit money from someone's account, and then credit to someone else's account, and you want to do that within the same transaction block. That wasn't a big ask for a good number of customers. So we took all of that in, and then we tied it into the architectural decisions. The first one, dynamic scaling, I'm going to jump into that in a second with slides, explain that, is using logical sharding so that you can easily rebalance your cluster and handle failures. That was how we architecturally tied the dynamic scaling decision into PG Shard itself. For the second take, simple to use, Jason's going to talk about that in detail. It's more, when you think about it, when you want to make that work with PostgreSQL and you have your distributed cluster, PostgreSQL's planner and executor are designed to read data off of disk or from memory and go over it. If you want to do the distributed stuff, there's a fair bit of functionality that's different. So you need to redo the planner and executor in a way that's both compatible with PostgreSQL and also fundamentally different. And Jason's going to talk about that soon. So I'll jump into the dynamic scaling part, and I'll start with an example that's more on the traditional partitioning part. Like I'll start with an example where you have the straightforward use case. I picked a click stream events table in here. It could really be anything. The idea is you have big data, you have 3 nodes, and you partition those. You partition this big data set into the 3 nodes. 1/3 of it goes to node 1, 1/3 of it goes to node 3, 1/3 of it goes to node 2. And the partitioning dimension could really be anything. It's time in here. The idea is, let's say you have terabytes of data, 1/3 of it goes to a single table or a single database on a particular machine. Any ideas how that's problematic from a scaling out perspective when you add new machines? Any guesses? Okay, I'll put that up. This is the most trivial and straightforward partitioning mechanism that people employ, and I'll put a new node here. And we have numbers, let's say 4 terabytes, 4 terabytes, 4 terabytes on each node. And when you want to scale this cluster out, this is extreme PowerPoint skills in here for us. What you're going to do is, you're going to move that data, a terabyte from each node, into a new node so you have an even balancing. The thing, evenly balanced cluster, the problem there is, you're transferring about a terabyte of data from each machine. You need to coordinate that. And you're going over a gigabit network. So this operation by itself is going to take hours. In the meantime, you may have network failures, you may have machine failures, so you'll need to think about that. And then you'll need to coordinate node 1, node 2, and node 3 to transfer that data to that new node. When you're at the 5th machine, you go through the same trouble again. So this is where you're trying to dynamically scale out your cluster. Another issue is, let's say you want to handle failures and you're replicating your data set and you have these big tables. In here, node 4 is an exact replica of node 1, node 5 is an exact replica of node 2, so you have this cluster set up. And let's see what happens when there's a failure. Let's say this is a temporary failure. What's going to end up happening is, the load on node 4 is more or less going to double. Like your other nodes are going to be evenly balanced, but then this guy is going to be taking the load. Node 1 should be taking 2 until it comes back up. If it doesn't come back up, you'll have to re-replicate 4 terabytes. So that's another challenge. Any questions so far? Does this make sense at a higher level? Any ideas on how to resolve this issue? Yeah, shard out. And the thing is, at 5 nodes, it's not very impressive. Imagine the use case where you have 100 machines, and then you have exact replicas of those machines, and you lose one of those nodes. You're suddenly bottlenecked on the failed machine's replica. You have a cluster of 100 machines, but you lost a machine and you're bottlenecked on that replica, so you don't get much out of having 100 machines in the cluster. And then here comes sharding. This is the architectural way to resolve this issue. I believe Hadoop, or HDFS, the Hadoop file system, is the first one to introduce this at the system level. Instead of sharding to the machines, you actually, previously you were partitioning into the machines, now we have much smaller shards in the cluster. And then when you want to rebalance the cluster, when we introduce a new node here, this is the rebalancing case. You're not transferring a terabyte of data over the network. We're saying let's take shard number 4, and in this case it's a half a gig, transfer it over. If we have a failure, that's okay, we can restart. And now this guy can start immediately start taking load. In fact, if we fail, we can restart from another node. So the operations that we're trying to do, they become much more flexible. This is the rebalancing case. So you have more flexibility when you have all of these shards in your system as to how you want to rebalance your cluster. Now, the second benefit, this is the replication case. Now we've replicated our shards. In here, it's round robin. It can also be random, the way we lay out the shards. And we have node 1, node 2, node 2 nodes are exact replicas of each other. Let's see what happens when we have a failure. So node 1 has failed. When we do this, let's say we have we have shard ID 1, that guy's load is going to go over to node number 2. We have shard ID number 6, that guy's load is going to go over to node number 6. We have 7, in here it's going to go to node number 7. So when you have a temporary failure in the system, you're suddenly not bottlenecked by any exact replica, the load gets evenly distributed to the cluster. If node 1 failed permanently, re-replicating those tables would also be much easier. And again, not so impressive when you have 6 nodes. When you have 100 nodes, it becomes very fundamental. You lose a machine, and then the load on the rest of the cluster increases by 1 or 2%. For how many of you guys this is already news? I'd just like to, for how many of the people in here this is new? For how many of the people this is old news? Okay. And here's how we represent the data in an example PG shard cluster. These worker nodes are PostgreSQL machines. Exact PostgreSQL machines, so there is nothing special in there. And then in PG shard we have a metadata server. This guy is where you create the PG shard extension. And that's all there is. So it's a regular PostgreSQL instance too. And the metadata server, you can also call it the coordinator node or the master node, has shard and shard placement metadata. And it's actually the authority on that metadata. If you look at it here, so it keeps the authoritative state. And that state is minimal, typically on the order of megabytes. You have 1 row per distributed table. As Josh showed in his demo, you have 1 row per shard and 1 row per shard placement. So it's 3 PostgreSQL tables. And then that metadata changes only when you create your distributed table and initialize your shards. You have a failure in the system, one of your worker nodes fails, and now you need to reflect that in the metadata. And you're rebalancing your shards in the cluster. So that's the only time when that metadata changes. The immediate follow-up question is what happens when there's a master node failure. I put down by the most amount of forward thinking at the top to the least amount of future thinking at the bottom. You can use streaming replication where the failure you will immediately fail over to the replica. On the cloud, we've seen customers use EBS volumes because this data is tiny. You can immediately spin up a new master node and then start issuing queries there. You can use standard PG down, PG-based backup tools to back that metadata up. Or in one case, we had a customer who did none of these, and then you write a script to reconstruct the metadata from the worker nodes. The last one isn't recommended. Still, it works. And I guess you can tell we haven't coordinated with Josh in terms of the demo. And then I figured I put this in because no SFPUG talk is complete without the PSQL stuff. This is how the metadata is laid out. As Josh noted, we have -2 billion to plus 4 billion in here. Hashed values, we support hash partitioning by default here. And then you kind of, where you have, say, a customer ID coming into the system, if you partition on the customer ID, we use PostgreSQL's hashing on that customer ID and map it to one of these values in here. That's how the whole sharding mechanism works. On the worker nodes are regular PostgreSQL databases. If you log into them, you're going to see, if you do /d, you're going to see your regular PostgreSQL tables. So one shard placement is one PostgreSQL table. We extend the table names by the shard ID. So if you have a shard ID of 1001 in the previous table, the way you're going to see that is like click events underscore 1001 to make sure that the shards are unique. And then, well, not only the shard table names are unique, but also index constraint names are unique. We also extend index and constraint names in the background. This is invisible to the user automatically when you're creating the shards. One thing to keep in mind is you create your index and constraint definitions, and then when you create the shards, they're all applied. If you want to create new indexes or shards, then you'll use a script to essentially, at the moment, to propagate that over to the shards that you have in your cluster. Worker node data failures. This talks about the data, not the logic itself. What happens when you have a worker node failure? We follow the simplest approach. We have a user-defined function that reconstructs or repairs shards. So you call that user-defined function, and then it repairs your shards. There is a question of what happens, how do we handle concurrent modifications during the rebuild phase? It depends on whether your inserts updates are commutative or not. This is one area where we're looking for feedback, so come and talk to us after the talk about your workloads and how you do inserts and updates, their nature. With that, I'll hand it over to Jason.
All right. And as has been said already, I'm Jason Petersen. I work at Citus with him, and once worked at Amazon on an infrastructure team, much as he did. I've been there about a year, and I'm one of the authors of PG Shard. So I'm going to talk about the logic for a little bit, because I think the way we've designed this sort of strikes a balance in terms of usability and also its feature set. It's a drop-in Postgres extension, which means you just say create extension, it's there. There's no crazy stuff going on with like a fork or anything like that. It is, you just have Postgres, you want to pick it up, start using it, good. You don't, get rid of it, it's fine, it's an extension. And we found that this was a common use case. So some people just need a little bit of this, they just want to get rolling, right? This is a great way to just pick it up and start using it. And they also don't want to have to use special functions to query their data, to change the way they fundamentally are doing stuff. They just want to use SQL, right? And a lot of these distributed key value systems you see out there have the concept of distribution fundamentally baked into their APIs, whereas SQL doesn't really have that concept, at least at a fundamental level in every single type of query. So that's sort of the balance we're trying to strike here. You want to support a subset of SQL, but without having to make people really change the dialect that they're talking in a day-to-day use of the application. So here's actually the invocation that sets up a PG shard distributed table. You just create extension, like I said, and then you create a normal table. Nothing special about it, no syntax extensions into the language here. We're just saying create this table, it creates a table. As Josh showed, it is actually kind of a shell table on the master. Then you invoke master create distributed table, which is a function that basically designates this table as being distributed, and you specify in that invocation the partition column that is going to be used to do the partitioning of this table's data. And then finally, you actually create the shards. So this takes care of reflecting the table schema, all the associated indices, all the constraints, and it extends them in such a way that they can be uniquely identified by the shard identifier, and then creates all of those using TBLs that have been executed on their remote worker machines. And the two final arguments you see there, one is the number of shards, so 16 here, and then the second one is the replication factor. So you could run with, replication factor of 1 if you want to, and essentially have RAID 0 on your cluster, or you could double it and have some failover semantics that'll kick in, and we'll talk about that in a second. So I don't know how many of you are familiar with the internals of Postgres or writing, against the C APIs it provides. But one of the wonderful things it gives us is hooks. And there are, I mean, probably well over a dozen by now. There's, you can take over any part of the command lifetime, planning, execution. They're very granular. You can do what starts up, the execution runs, like finishes, cleanup, all that kind of stuff. But there's not really a hugely strict contract on what specifically you must do by the end of that invocation. You can be a nice citizen and you can chain them, so that way you could actually have basically like a stack, like kind of a chain pattern of extensions calling one after another, or you could do something radical and completely hijack the entire process of execution to do something, say, distributed with query planning. So this gives us a very kind of first-class way of hooking into the Postgres system, and so you can just load up the extension and it's there. So let's go into what the planning phase looks like. First of all, we examine the query, which basically we're getting a raw query that's had minimal processing, parsing, and a little bit of processing applied to it, and we figure out if it's distributed by looking at whether or not it references any of the tables we know to be distributed. If it does not, then we can just fall through to PostgreSQL. And what this enables is a hybrid approach, wherein your master could actually have a set of normal tables that, let's say, you use the relational model on with an ORM or something, and then maybe you only have 1 or 2 tables that you want to blast across 100 nodes because you have some huge like document database or time series analytic database or something that you'd like to have in your machine. But the great part is there's one interface, and it's Postgres. And so then we look at the queries, the parts of it, and we try to figure out which shards are involved in the query. For an update, a delete, a select, obviously this is something in the where clauses. For an insert, it can be one of the column values. And based on this, we can determine if a single shard's involved, or many shards. We can even determine errors, or maybe you've completely ruled out all the shards. And at this point, we call into the Postgres native deparsing libraries to take that query and basically modify it just so it has that shard identifier in it, and then we spit it back out to SQL that we can essentially route out to the machines. So here's a little detailed example. You get a query coming in saying to insert, let's say you have a big customer reviews database, and there are the values. We say, oh, you wanted to partition this table on customer ID. There it is. We hash it. We find which of the shards contains the hash value for this column value. And then once we've determined, let's say it's shard 16, we basically reproduce the SQL using this new shard identifier in such a way that it can uniquely identify the shard. And this is important because, as you saw with Ozgun's part of the presentation, a node contains many shards. So if we just use a table name, that's not enough. You need to know which shard on that node is actually the one being created here. And it's worth mentioning in step 2, the part that does this decision making is actually the same constraint exclusion mechanism that's used within Postgres core to make determinations about partition planning, for instance. So we try to be good first-class citizens in terms of recycling the logic used by Postgres. And then there's the part about the actual execution. And you have to be a little bit careful here because it's a distributed system. You've got a lot of things going through. There's parallelism. And so we have to think about what the safe commutation is on the set of operations that can be performed. So for instance, you can commute selects with inserts, generally okay if you're willing to relax isolation a little bit. We do have full consistency on writes, which means you write something, you're going to see it when you read it back. There's none of this kind of, simple DB type document store where you may get like stale data on one call and then fresh and then stale. There's none of this kind of flapping. And the replicas do have to be kind of visited in order to also make constraints work properly. And that's sort of the technicality we discovered. And if any query succeeds during a modification, if any of the nodes succeed, then the entire query is successful. It's possible to have one replica succeed, all the other ones fail, and then you just basically mark them as bad, but the client is none the wiser. They know that their data got written. So here we go. We've got a shard. Data comes in. It's determined to go to shard 6. And so basically we send it to all the shards, as I said. In this case, we have a replication factor of 2, so it's going out to 2 of the nodes. And let's say worker node 3 fails entirely. But worker node 1 succeeds. So we can return the query as successful, and then basically, when the query is wrapping up, the master node needs to do a little bit of bookkeeping. And so it's going to go in its internal catalog of all this stuff and mark node 3 as needing repair, which is currently a user-defined function that needs to be manually invoked. But it will, copy all the data from worker node 1 over to worker node 3, rebuild the table with the DDL, and basically let you be on your way. As I said, the modification semantics, consistency in terms of read your own rights, the flapping of some of these looser consistency models. The safety comes from the commutativity rules. Selects and inserts can be reordered. Update, delete obviously cannot, but the locking's done on a per shard basis. So if you have 100 shards, for instance, you're going to be able to still have pretty good concurrency here. And uniqueness constraints, I said there's some issues with making sure inserts visit the shards replicas in a consistent order, but that's all taken care of. Single shard selects are kind of the opposite of the inserts because they only need to read from one thing, right? So you kind of get the speed of that. And you can also dynamically fail over to the replica, so there's no retry required from the client side. And the common pattern here is kind of a key value access pattern. You know what you're going to look up. You've got an ID. Maybe you want a JSON blob, as Josh pointed out. So here you get it coming in. You look at the where clause. You figure out where it's going to route the query. You can really think of the master as just kind of a coordinator or router that is not storing any data. It's kind of dumb in the sense that it's not doing any SQL execution directly, but what it is doing is keeping track of the failures, concurrency control, state of the machine's health, all those kinds of things. And it finds out that it's in shard 3, routes over there, fails. The top level query is still in effect here. We haven't returned anything with the client. We're going to fail over to worker node number 3, get that data, return it to the client. The client's none the wiser that the failover just happened. Maybe it's a transient failure, so we're not even going to modify the metadata because there's no divergence in the shards data set right now. And it's also worth noting that there's a connection pool that's per session from the client's view. So if you have a long-running session, you're going to be able to recycle those connections to all the nodes in the cluster, which means that there's no setup and teardown time in terms of actually getting connected to all your nodes. And Josh also, he demonstrated a multi-shard select, and this is included in Peachy Shard in kind of a rudimentary way. We do pull the data from all the shards, and we put it in a temporary table locally, and then basically re-execute the original plan on that temporary table, which allows the aggregates and the sorts and things like that, groupings, to take place locally and return in identical queries though they were local. One thing to point out here is that we do calculate specifically which columns are necessary and only pull those to the master. So for account star, you're essentially sending a bunch of blank rows over to allow that aggregation.
Well, if you're on the dev branch.
If you're on the dev branch. So the dev branch isn't something special. This is on GitHub, so just go there, build the develop branch. All right, we've got full coverage, Travis, all that kind of stuff. It's not some bleeding edge thing. You can build it, it works. And yeah, it has corrected that. We're on track for 1.1, probably next month or two. But yeah, so it will pull down exactly the columns it needs, and if it doesn't need them, you're not going to sit there wasting a ton of bandwidth. Citus, on the other hand, takes a more fundamental model here. It actually will push down the aggregates. For example, an average may return a tuple that's actually a count and a sum. So each individual node is actually fully exploiting its computational potential before it's returned to the master, where final coalescing needs to take place. You can maybe kind of think of it as I don't know, like MapReduce, but is this dying? Hello? Okay. But the great thing here is that these guys are compatible, right? Peachy Shard works with Postgres 9.3, 9.4, and CitusDB, and is completely interchangeable with the metadata format. So you can use one to do all of your inserts, updates, deletes, the real-time ingest of the data, and CitusDB can do these fancy analytical queries that honestly are, may take 30 minutes on a more traditional non-distributed database, and it supports joins. So that's the sales pitch there. Limitations here. Transactions cannot involve multiple shards. So you want to do two things on two different shards. As we said, no transaction there. Span multiple statements. So right now it's kind of a one-shot thing. You've got your typical CRUD operations, your insert, update, delete, select. But it's best to think of this as kind of either document store style with the identifier and the JSON-B type thing, or if it were some sort of analytical database. I'm 2 slides from the end. I'll catch you in a second. No join support, and cross-shard constraints are unenforced. So if you have a uniqueness constraint on a column that's not the partition column, there's no way of enforcing that across the cluster right now. Upcoming features. So we're really looking for like what is keeping anyone from using this. Would you need more SQL coverage? Do you want automatic rebalancing? A multi-master. So if you have a ton of data, you can get it in there, but if you need to get it in there quickly, the write throughput through a single node is going to be a bottleneck. So multi-master is one solution there. Range partitioning, we alluded to earlier. And auto recovery, automatically repairing nodes as they fall down, some kind of background process. Or anything else that could make this a viable solution for you. We're definitely taking feature requests. It's on GitHub. Fundamentally, many small logical shards to facilitate future rebalancing work. Implemented with the standard hooks, first-class citizen of Postgres. It's an extension, create a table, distribute. It's that easy. And it tastes great with JSONB. And can, if you want to just maintain one database, use this for your non-relational stuff. Use the relational parts of Postgres for the relational stuff. You don't need to go install some exotic NoSQL thing. Here's our contact information, and Sumit is also here. He's another author of the extension. And we'll open up for questions.
Do you support executing function calls?
Do we support executing function calls? You mean like if a function call appears within the text of a statement, or like?
Well, okay. Yeah, I guess we would then.
Yeah. I mean, yes, we support executing function calls. There are obviously some caveats with modifiers, like if it's immutable versus volatile, those kinds of things, but that's fully supported. All the types are supported, all the stuff that Postgres supports, this supports.
Other things like alter, reindex, like that kind of stuff.
Alter, reindex. So you're asking about a DDL commands are supported?
Reindex, yeah.
No, right now DDL commands are not automatically pushed down. So, it's a single shot schema right now. That's not even something I thought up for my, future request, but modifying the schema on the fly is something that would be considered.
Yeah, we have a script for that, and I guess we could turn that into a user-defined function.
All right. I saw something up there. Yeah.
Do we support the copy statement?
Do we support the copy statement? Not at the moment. I do have again a script that basically will transform that into a method that will allow you to. It will transparently let you use copy, but it's not optimized right now. We have something on our backlog right now to make a fully optimized copy in order to do bulk ingest.
What happens if one node is just slow?
If it's what?
So you have distributed, you have a bunch of nodes, but one node for some reason, someone else is playing with it. It's slow. At what point do you give up and decide there's a whole variable for that?
I see. So obviously that could be the timeout settings on the client itself, but there is no long-term tracking of node health as a basis of response time or something. So if you have a brownout on a node, that's not something we're going to detect. Are you just saying one is particularly pathologically bad?
I guess what I'm saying is, if you have, say, you're fanning out to 100 nodes, one of them is not happy. At what point, if it was just down and you couldn't connect, you would just mark it inactive and return the results when it's mirrored.
Yes.
But if it just hangs, what happens?
I mean, if it hangs long enough, right, you're going to get an error and we mark it as bad.
It's going to time out.
If it times out, right?
It's going to time out inside the grid.
It'll time out inside our connection, yes. It would time out.
Result of the client.
Right.
And that's configurable?
I'm not sure what level of that's configurable. I'd have to think about that. But a configuration for the backend connections is certainly something that we could tune. I think right now it's set to some number of seconds, and then if it drops out, then we're going to mark it as inactive and just stop paying attention to it. But a brownout detection for something that's just kind of a little bit slow, that's not something we would track. I think you might want to just have a separate monitoring solution on all the nodes and say, this machine looks like something's up with it, right?
Is your timeout, is the timeout a number above and beyond the other node's response time, or how do you? How are you telling between the timeout and the...
Well, no, there are two timeouts, right? So there's the backend timeout libpq between us and the worker node, and then there's also the client's timeout, which the client is completely configured.
Sure.
So if the client comes to us and says, 100 milliseconds, if it takes 2 seconds, we're not going to satisfy that. That'll drop on the client side. Also, if ours is set to, I think 5 seconds, maybe 10, that's something maybe faster.
It's somehow defined that you can change in the code right now. I don't remember the default value.
Oh, that's right. Yeah. So right now, it's in the PG shard code as a confifying. It can be taken out to a global user configure variable or something like that.
when you mark the partition as inactive, will you not try it again?
Right now it's a one-shot thing, so if we fail to write to, like, so the thing is if you write to one partition and fail to write to a second one, we don't immediately retry, no. So there is no immediate retry on that.
And then the next query, the next time an insert comes in for that,
You're not going to try it out.
We can't respect that replica anymore because it's diverged, right? So we have to mark it as inactive and then repair it.
What is the repair mechanism? Are you doing a logical dump of the other shard?
Yeah, I mean, basically we drop the table, we rebuild it, and then we do a copy between nodes to pull over all of that data. And as he said, you know, inserts can still occur to both of those tables. It's just the updates and deletes get blocked out from that shard during the repair process. So the master establishes connection to the workers on demand as needed within the session, and then caches them during that session's lifetime. So the first time you hit a node, it's going to need to establish a connection, but it does it on a per node basis, so it's not like per shard or something like that. So, you know, if you have 100 nodes, you're going to have 100 connections potentially building up in there. You know, if that becomes pathological, that's obviously something we would look into cycling or something like that. And you know, due to the architectural limitations of Postgres, doing a shared connection pool across processes might be a bit difficult. So right now it's per session. Wrapping up, or?
Yep. I'm sure it's documented, but I didn't see any coverage of how you actually specify the nodes.
You do not specify them directly. Oh, you're saying the initial
How do you
list.
tell, yeah, when you
Okay, so
create-
that's
how
in
do you
your
tell
PG
how
data
it's
directory. There's, yeah, I guess Josh.
wait, let me in PGA, I can actually show you this.
Okay, I don't know if we're going to wait for the
I can actually show you
PGA.
this.
It's pretty straightforward. It's a host file in the PG data directory with a list of you know, host names, ports, that kind of stuff. And I believe you got it working with a PG pass file to do authentication too. Here, let me.
Yeah. Okay, that was fun.
As far as logical shards, is that like they're always constant size, or is it constant number of them?
Here, I'll let this can take that.
Yeah. In this one, you specify the number of shards that you want to have ahead of time. So you say, here's my table in the user-defined function that Jason showed. I want to have 128 shards, and we recommend that you start with a large enough shard count that as you scale out your cluster, you're going to have enough CPU cores, one CPU core per shard. So let's say you have 16 CPU cores in your cluster, we'd recommend that you start with 128 shards. That way you can scale out your cluster to 128 CPU cores. So as it stands, you just specify it as you're initializing the table, as you're distributing your table. Does that answer your question?
Yeah. Okay.
What if you're hashing on a value that is particularly variable in size? Like you might have one shard that is like way bigger than another shard. What do you recommend for that?
Composite types, like hashing on the composite type would be one solution. If you have, in the case of Amazon, this was like the robot session ID. So session ID 0 equals to robots. If you have that use case, then you won't currently handle it in PG shard. If you have a second dimension that you can partition the data on, that should evenly split out. Could you repeat the question? Well, the current way is, there are two ways. One is you issue all these insert statements into the cluster and they get loaded in. A second way is, I don't know if it's public, you could use the copy command. Jason has a trigger, like this is behind the covers, it's an open feature. You call the copy command behind the covers, it routes that into an insert that does the load, so if you want to use the copy command. Yeah.
So you configure the shards in this pgworkerlist.conf, and this actually needs to go in PG data, not a configuration directory if you've got a separate configuration directory. So the PG worker list is really simple. We have a shard, and I've set up a fake DNS on this, so I can just name all the shards instead of needing to address them by IP address and a port, and that's it.
Database doesn't matter, or is it a different database?
It always connects to the database that the table was in.
Okay.
And so you can't actually have a different database name.
Okay. So scale proxy configures this in a table, which is kind of nice actually.
Yeah.
The problem with things stuck in here is it's hard to update when you move something else.
In Citus DB, you can update it and send Citus DB a SICUP. We currently don't have it in PG Shard. The idea is it's similar to PGHBA conf. The format of it is also similar to PGHBA conf. You update it, you send a SICUP. Last question, if anyone has questions, and then we have. Go ahead.
Can you do a PG dump from the master?
Yes, you can. And then you'll get the metadata tables and any other tables that you have on the master node.
Is that recommended?
There is one glitch, if you will, in terms of the logical relation ID name. I'll let Jason, when you do a PG dump from the master node and now you get the metadata tables, when you reconstruct it, if it's the same table, does it?
Yeah, so the problem there is right now, as you saw in the table, not this table, but another one, the OID is being stored to reference the relation that's being distributed. And so if you dump and restore, there's no guarantee that the OID is going to remain across the restore. And so there's an open issue that I opened against ourselves to make sure that that gets spit out in a textual format. I think just casting it to red class or something like that will make sure that when it's restored, it'll, under the covers still technically be an OID, but it will make sure that the PG restore works correctly.
So it's coming up. It will be recommended in our e-course.
Yeah.
Yeah. Cool. We have 2